Welcome to another installment of Data Skeptic Animal Intelligence. Today we're revisiting a topic you heard about a few weeks ago, albeit from different perspectives. We're getting back into Satbird, a benchmark data set for bird species distribution modeling, specifically around remote sensing. We discuss more about the data set itself, the modeling process, and challenges faced with what isn't quite, I guess it is imbalanced data. They have US data and they have Kenyan data, but there are some subtleties that had to be worked with. We get into all that and more during the interview.
My name is Mélisande Teng, and I am a PhD candidate at Université de Montréal, working on AI for biodiversity monitoring. My work mostly is at the intersection of remote sensing and computer vision for biodiversity monitoring. So one of my main projects has been to work on this data set called Satbird, which is a data set for bird distribution modeling using satellite images and environmental data and citizen science data. I also work on tree monitoring in Quebec plantations using drone imagery in partnership with a biologist here called Etienne Laliberté. And I've dabbled a bit in bioacoustics as well.
Maybe for listeners who aren't familiar with it, could you share some details on what remote sensing is?
Remote sensing relates to, well, anything that you can sense remotely. So that encompasses, using satellite or drone imagery that also can refer to using recording devices like autonomous recording units, which are used a lot in passive acoustic monitoring.
And when you talk about satellite imagery specifically, in my head, I get the idea of like a picture, like it's a PNG file or something like that. But I know it has at least a little bit of metadata, like a latitude and longitude and stuff like that. What do you look at when you think about satellite data?
I think there are many different advantages of satellite imagery. So first of all, now we have programs like Landsat and Sentinel, which enables us to have data all over the globe. But mostly, you also have access to more bands than just the usual RGB bands that you have with normal pictures that you take. So you can have access to multispectral or hyperspectral data, which is just more bands of things that the human eye cannot necessarily see. So, for example, in plant monitoring, this is really important because the plants will reflect different bands that we don't necessarily see. I feel like this is a lot of information that can be leveraged in many ways. Yeah, I'm going to do a little bit of a digression, but I'm a huge fan of the work that has been done recently around location embeddings. So how to actually include geographical information into your models to kind of get a sense of, what is a representation of geography of the Earth as a sphere, using latitude and longitude. With one collaborator, we're also working on including spatial dimension into to have kind of time-space embedding and get a model of spatio-temporal Earth, basically.
So I know the idea of an embedding really well in natural language processing, where you give it some text and it embeds that as a number. And the nice feature, at least in NLP, is that two words that maybe are spelled very differently but mean a similar thing end up in a similar place in the embedding. And that also, there's some fancier features beyond that, that the embedding puts them in a smart location. I'm not totally clear on what a location embedding does for us. Could you share some use cases?
So location embeddings have been used in different sorts of tasks. I mean, some of them are toy tasks, but for example, for climate modeling, you can imagine that, well, most of the time people use some sort of environmental data and so on, but including latitude and longitude should also help the models. The challenge here is that if you just do a linear encoding, that doesn't really work because the Earth is spherical. So then you will run into multiple issues at the poles. So people have come up with spherical harmonics to encode latitude and longitude. Yeah, to kind of respect the geometry of the Earth in some sense.
And could we talk about the origins of Satbird? How did the project get started?
Well, the project started because we were looking at species distribution modeling. I think what right now the most popular method that is used is still Maxent in the context of presence only data. So it means opportunistic data. So it means that if you go to a certain place and you report what you have seen, you have presence data, but you don't necessarily report what you have not seen. And so Maxent is like one of the most popular method used by ecologists, well, mostly because it works pretty well, but it has many limitations. For example, well, it's suited for presence only data, which, is fine, but it doesn't extrapolate very well to places in which the environmental conditions are quite different from what it was trained on. It hasn't been used so extensively for modeling many species at once. I guess it's also mostly used because there's a nice R package, and then people like to use it because the package is here and ecologists use R. But one of the main limitations of traditional models for species distribution modeling in ecology is that, well, they often rely on environmental data and field survey data for the species data. And those can be limited in their availability, both in like time and space, and also of species that are reported at a larger scale than traditional studies that are done. So the idea here was to use satellite imagery and also citizen science data to model the distribution of bird species and try to see, well, satellite imagery is available everywhere and it's pretty cheap and it's available at a finer resolution than the traditional environmental variables that are used. So can we actually, try to see if we incorporate this into models on top of the usual environmental data, can we get an improvement on the species distribution prediction? Now, it's not completely new to use remote sensing for species distribution modeling. Ecologists have done this before by deriving indices from remote sensing data, but it's kind of hand-derived indices. So they would look at the vegetation index, water index, NDVI and NDWI and other things. But we really wanted to see, what if we actually put a patch of the image now that we also have access to convolutions and make the models a bit more lightweight than what they are, because the current models were not meant to support predicting many species at once. But we know that species interact, so knowing the distribution of a certain set of species can also inform, knowing the distribution of other species. Can we try to incorporate remote sensing in a way that is more effective, and can we actually improve the models for predicting bird species distribution? Now, the other thing that I was very excited about when I started the project was we're going to use citizen science data, and we started with eBird because it's this citizen science platform that is particular because it has a big community around it, first of all. So people report like lots and lots of bird observations every year. And it also has presence absence data, which is kind of rarer to get with field surveys. It's usually like quite expensive to send people out on the field, and then it's like limited in time and space what you can actually get with a team of people who go out on the field. And I also like this idea of using citizen science because for me, I see like science as a way to empower people, and so it's nice to use science produced by citizens, but also try to make a tool that can also give back to them, because eBird has been so great at maintaining their community and also like giving them tools so that they learn more about birds. It can also help them in their birding. I think our first ambition with Satbird was to say, well, first, okay, let's try to investigate whether we can use remote sensing to improve species distribution models, but also, if it works, can we try to integrate it at some point in eBird to kind of suggest species that could be there in places where no one has been? Because the goal of Satbird was to use satellite imagery that is available everywhere and environmental data to predict bird species encounter rates.
As a data scientist, I'm pretty much glued to my desk, and I know the struggle of balancing work and wellness. That's why I'm excited about Factor's no prep, no mess meals. I cannot cook every day, and these are perfect for those of us who need smart, easy choices to fuel our busy days. Factor has 35 different restaurant quality meals and more than 60 add-ons to choose from, so you'll always have new flavors to explore, and they have categories to fit every diet. The best part is that these meals are ready in just 2 minutes. That means even on my busiest days analyzing data, I can enjoy a nutritious, great-tasting meal without disrupting my workflow. It's the smart solution for people like me who need to optimize our time and our health. Head to factormeals.com/dataskeptic50 and use code dataskeptic50 to get 50% off your first box plus 20% off your next month. That's code dataskeptic50 at factormeals.com/dataskeptic50. Again, to get 50% off your first box plus 20% off your next month while your subscription is active. I recently found a solution, and this service is called Delete Me. Delete Me is a subscription service that removes your personal information from hundreds of data brokers. While I myself have not been the victim of identity theft, I know several personal friends that have. On a personal level, I get harassed and scammed all the time. I hardly pick up my phone anymore. Or at least that's how it used to be until I found Delete Me. Getting off those data broker sites has reduced spam and robocalls. Ever wonder how much of your personal data is out there on the internet for everyone to see? More than you'd think. Delete Me knows how to find it and get it taken down. They'll take you out of the largest people search databases on the web, and in the process, help prevent potential ID theft, doxing, and phishing scams. Sign up and provide Delete Me with exactly what information you want deleted, and their experts take it from there. They send you regular personalized privacy reports on what they found and removed, and they continuously do this. It's not just a one-time cleanup. They're constantly monitoring and removing your personal information. Take control of your data like I did and keep your private life private by signing up for Delete Me. Now at a special discount for Data Skeptic listeners, you can get 20% off your Delete Me plan by texting DATA to 64,000. That's text DATA to 64,000. That's the only way to get your 20% off is to text DATA to 64,000. One more time, that's DATA to 64,000. Message and data rates may apply. See terms for details. Well, I know for many satellite images, a single pixel, even though satellites do give us detailed data, a pixel could be several meters in size in a lot of cases. So, you're not going to see an individual example of a species. I guess the resolution just isn't quite there. What is the information content you get from the remote sensing data?
Well, what we really wanted to see if we could get was actually information about habitat. So there are usually like two things that people are interested in when they look at species distribution. It's geographical range, which tells you where geographically a species can be found. But, that doesn't tell you whether if I go to a specific place in this region, I will see a pigeon or not. And for that, you would need to have the habitat, which is basically like all the environmental conditions that should be there for species to thrive. Of course, like satellite imagery, it's not available at the resolution at which you could see the bird in it, but it's still like 10 meters resolution. We use Sentinel-2, and we believe that was probably enough to get a more precise information about habitat than what we usually get with environmental data. Environmental data is like the one that we used was 1 kilometer resolution, and then the finest one, 250 meters resolution.
So in terms of determining habitat from, a single remote sensing observation, is that like a traditional machine learning classification task where maybe you have 10 different habitat types and you want to label each image, or is it something more complicated than that?
Actually, we're not predicting habitat with Satbird. Like what we're outputting is directly the bird species encounter rates for over 600 species at once in the US. But we're not looking at, what type of habitat it is necessarily, because there's also like no real ground truth for habitats. I mean, I guess you could find like some information about land use, but this is not quite habitat because like some species, for example, they only breed in, I don't know, young jack pine forests. and that like you wouldn't have this information in land use data. Although maybe you could try to use that as additional information in the model, but we thought, okay, maybe in the satellite imagery you can see trees, you can have like some idea of what kind of land use you have in there. So yeah, we didn't really investigate this further.
And could we talk a little bit about Satbird as a data set? How many observations are in it, and what does an observation consist of?
Actually, Satbird consists of three sub data sets in some sense. We took two regions of focus, the US, because that's where you have most observations in eBird. And so that was our best case scenario to test whether satellite imagery actually made the difference. And then we also looked at Kenya as a region that is like extremely biodiverse, but in which you have very few observations. For the US, you will say, well, birds migrate. So we consider two seasons, June, July, which is about like breeding season, and then December, January. As for the number of observations, for the biggest sub data set, which is the US summer data set, we have about 120,000 observations. About observations, I mean hotspots, which are observation locations at which people reported birds observation records. At each location, we have access to, well, the satellite imagery patch. So, well, if it's in the summer, it's the most recent satellite image from the summer that has like the least cloud cover as well. And then you also have access to environmental data that we took from WorldClim and SoilGrid. So that contains pedological data like pH of the soil and so on, and then bioclimatic variables such as temperature and precipitation. On top of that, well, we have the targets that we're trying to predict. And for that, that means the bird species encounter rates for in the US, like over 600 species. And those are computed using complete checklists from eBird. And those complete checklists are basically reports of presence absence at a given hotspot. And people, like multiple people, will report one or maybe more checklists at this hotspot, like on different days. But we consider like all of June and July. And so we aggregated all the checklists over, I think, about like 10 years in this season. And basically, the encounter rate is computed as the number of checklists at a certain place that report a given species over the total number of checklists reported in that place. So it gives you the probability of, if you go to that place, are you going to see the species or not? Yeah, additionally, when it was available for like certain species, we also extracted range maps information from eBird to kind of help a bit the model, because some species have eastern and western variations and they have the same habitat, but then they're never going to be found in the same place. And so that's this concept of geographic range that I mentioned earlier. So they might have the same habitat, but not the same geographic range. And so if we can help the model with knowledge that we already have from experts, then why not?
Well, let's get to the big question. To what degree does remote sensing data help improve species distribution models?
Oh, I think that's a very general question. I don't think that's very generalizable to everything, and there's so much to look at and to discover with like more species and so on. I think it's a bit of a not case by case. Like we have seen like some, I wouldn't say like trans plural because it's just Satbird, but some things that could hint that satellite imagery is actually really helpful in some cases. Like this is not going to be a general conclusion on things, but what we've seen on Satbird at least is that, well, if you use satellite imagery alone without the environmental data, it doesn't do better than using the environmental data alone. So the models that actually just use environmental data, so bioclimatic and pedological data, already do pretty well. But if you combine satellite and environmental data, then you actually get an improvement over models that use either of those modalities. It gave us a hope that this is a promising avenue, just because you can maybe get some complementarity between the two sources of data. Now, the results on the Kenya dataset were a bit less clear, as in, general conclusions were about the same, but satellite imagery didn't help as much as it did in the US. But there are many confounding factors, I think, to the performance of the models in Kenya, but mostly because there are really not a lot of observations. Data scarcity is the first thing to look at. And so maybe, there could be other methods that are more suited in places where you're in a low data regime.
Could you share some general details on the modeling steps? What do you have to do from your raw data to get it to its most usable form?
Actually, when we presented Satbird, we presented it as a data set and benchmark, and so it was kind of first baselines that then people can try to improve. So we actually didn't do that much, processing. There were a few design choices that we made that I feel a lot of people can improve on. For example, we decided to use patches of satellite imagery that are 64 by 64 pixels that we then resize to whatever was the size that we needed to put in the model, but that corresponds to 640 meters square region centered on the hotspots of interest. So you could say, why is it this and not 1 kilometer square or 2 kilometers square? I mean, we had to, we tried different things. I think we set on that because I don't know, there's also, you'll notice that it's 64, so it's like the very computer sciencey bias of having a power of 2 somewhere. But I guess ultimately, this choice was a bit guided by, okay, we have hotspots in eBird for which we have a certain latitude and longitude, but obviously, like, many people report to the same hotspot, but not everybody is exactly at the same latitude and longitude when they report this. Because, like, a hotspot sometimes is identified as, I don't know, like this statue in this park. But, people can be 15 meters away from it or 30 meters away from it. And so we need to have a bit of buffer because some locations are really not precise. It's also about, like, yeah, the habitat of the species, like what scale is important for a given species, and obviously, like, this choice is not, maybe might not be suited for all the species that we looked at, but we thought, okay, maybe this is big enough that you get relevant information for all the species. But to go back on the data processing part, so yeah, as I mentioned, not too much data processing. I guess most of the work went into building this data set and actually framing the task and transforming this raw eBird data observations into really defining, we want to look at presence absence data. And what is very unique here is that we're predicting directly species encounter rates as a value, as a probability directly, not just binary observation of 0 and 1. Yeah, I wouldn't say there's like that much processing. I mean, obviously, the general like normalization and aligning the environmental data with the satellite data as well. But beyond that, there's not like we didn't do crazy data augmentation and stuff.
Could you share some details on the methodologies you found most fruitful in the modeling stages?
Okay, so one of the models that was performing best is actually a ResNet 18 architecture that we initialized with ImageNet weights. Now we actually, tried to compare whether it was better to train from scratch completely or initialize it with weights from models that were trained on satellite imagery as well. Yeah, we found that it wasn't actually much better to initialize those weights with models that were available that were trained on remote sensing data. And actually, one of the reasons is that the models that we tried to initialize our ResNet with were trained on aerial imagery. I mean, I believe that's one of the reasons. And aerial imagery, even though it kind of looks similar to satellite imagery, it's actually not the same type of sensing and like gathering the images. I think that that's one of the main reasons, and it wasn't trained on the same resolution. And I think there were other works that showed that it wasn't so transferable between like different tasks if you tried something on a very different resolution than what it had been trained on. I mean, other modeling choices that we made also included, well, including the range maps in the process. Obviously, like it doesn't make a very huge difference because ultimately, I think that the model is still able to pick up things from environmental and satellite imagery. The range maps were kind of just used as post processing masks, but then that would just zero out species that are not supposed to be there, but because we predicted a lot of species at once. I think if you average metrics over all the species, then you won't see that big of a difference because maybe you will zero out, I don't know, 10 species in a given place. Another thing that we tried was actually on the data set for Kenya, but as I mentioned, the results were not so it wasn't so clear whether satellite imagery was really helpful. What we tried to look at is incorporating the information of the number of checklists that are in a given place. So I mentioned that when we look at the encounter rates, we actually average over the number of complete checklists that are present in that place. But obviously, if you have, two checklists, then there's only three possible numbers for encounter rates. Like you would have 0, 50%, or 100%. Whereas, in places where you have more checklists, then you have a, let's say, more accurate representation of what the actual encounter rate is. And for the US, we could afford to only keep hotspots that had more than 5 checklists. But in Kenya, because data was so scarce, we had to keep everything, which meant that, in some places you just have one checklist. So, that gives you a certain representation of what can be found there, but it's not a complete picture. And so we tried to have a loss that included this information and that kind of weighed hotspots that had more observations more, that to give them just more importance and say, this is a more reliable data point in some sense. Yeah, so we came up with this kind of weighted loss, tried different strategies to put more weight on locations that had more observations. It did make a bit of a difference, but as I said, like the baseline result was not as high as what we can get in the US just because we have more observations there. I'm not really able to say whether this is a strategy that actually works. I think it would have to be tested in other cases.
So I know the Kenya results aren't clear, but they're also quite sparse, and we can't conclude so much from sparse data. How much data would you need to feel more conclusive about results and maybe come up with better models?
I don't know. This is tricky. It's also that the Kenya data, like if you look at the distribution, it's very like concentrated in certain places, and then you don't have data in like many places elsewhere. Oh, one thing we had also tried doing is initializing the weights of a model like trained for Kenya, like initializing the weights with the models trained on the US data, but it didn't really make much of a difference with training from scratch. Actually, training from scratch was better. I'm not quite sure like how much data we would need. My take on it is more that in those cases what where you need to put the money and the effort is a bit into looking at methods, maybe in like future learning or something, but put most of the like means into like data collection. Because ultimately we can build like whatever machine learning model we want, but we'll still need to have evaluation. So if you don't even have data for evaluation, then how are you going to say that this model can be helpful for in informing any kind of decision on conservation ultimately? I vote for more data collection.
Good suggestion, definitely. I believe you mentioned ResNet architecture was one of the more promising approaches. ResNet's a deep learning architecture, and one criticism people will have of all deep learning is that because there are so many parameters, it's kind of a black box. Maybe we know it works or how good it works, but we don't always know why it works. Do you have clarity into why your model works?
Well, I would say it works because it uses environment like more data that was usually used in species distribution models. and being able to also have this data at a fine resolution and all over the globe is kind of amazing, even though we mostly focus on the US. And also, like, I just want to say that we use ResNet, but we could have used something else. It was just, let's try to use an architecture that is not too complicated and that people have used extensively before. I feel that even now, ResNet are kind of seen as the easiest choice you can do for CNN these days. I mean, it's true that right now we haven't focused on, much on explaining everything about like what our model does, but we are planning on, making more ecological analysis of the predictions of the model to kind of, maybe look at different species specifically that interact and see, okay, is the model able to like pick up those things? But, that's more of validation, obviously, than anything else. But I would say, the thing is, it's not about the model like being a black box or something like what. So, for example, our ultimate goal is that, well, we bring this work to ecologists, and we have had discussions with ecologists already. But we bring this method to them, and then they can see, oh, okay, I can use satellite imagery to improve my species distribution models, and maybe they will either use the model as is, but also mostly, I hope just improve it, like using their own domain expertise. It's not so much a problem that not everything is explainable, but where we need to put in the work is actually in the translation between the vocabulary of computer scientists and then the vocabulary of ecologists if we want to make a bridge between those two disciplines.
And you'd mentioned that Satbird is really a benchmark, and that maybe other researchers will come up with new innovations and make better predictions. Could you share some of your vision for that? Maybe what direction that might go in, or just ways in which the benchmark could be supplanted and beaten by a little bit more effort or different modeling techniques.
So I think I see two streams of impact with Satbird. So, one in the machine learning community. So like people can say, oh, this is a cool problem in like computer vision. So I can try to like apply my, different methods and so on, like to improve species distribution modeling. And then it's like an important application. So I might as well, try that on top of trying my method on, I don't know, more usual benchmark tasks. On the ecology side, like I'm very aware of the limitations of Satbird. I don't expect an ecologist to suddenly be like, oh, this is such an interesting task. Now I'm gonna like shift my research and do this and do machine learning. But it's more a way to say, hey, like people in machine learning are developing these methods for a problem that might be very close to what you're looking at. Or, maybe Satbird, it's not the data set that you're using, but there's a way that you can frame the like your specific problem in a way that is, similar to the problem that we're trying to solve with Satbird. And so then you could use like this method. Yeah, I guess my primary goal was kind of to build a bridge between these two communities and also maybe open up more exploration possibilities for species distribution modeling beyond what was done by ecologists.
You'd mentioned that the models are really not just meant to predict one species, but many species. I think even up to 600 are covered.
Mhm.
Could you share some details on the challenge of modeling something at that scale?
Yeah, so that's actually called joint species distribution modeling, and there are different ways that people traditionally approach it. So some methods in ecology, what they do is actually one model per species and then stack the models and say, this is a stacked joint species distribution model, but that obviously doesn't take into account any interaction or co-occurrence between species. The main challenge with traditional methods in ecology when you try to do, I mean, I hate to say large scale because like large is very relative, I think, and people in machine learning are like 600 species. Oh, that's not large. But then you're like in ecology, wow, that's a lot. Okay, so if you try to do things at a larger scale, then the traditional models are just not computationally suited for that. It just crashes. Well, I think one of the main challenges when you model like many, many species at once is that obviously, if you go to a specific place, you're not going to have all 600 species present. But yeah, so you will have a lot of zeros in your target, and then a model that predicts just zeros might do very well. So I don't know. These are like considerations to take into account, and then obviously, there's a higher chance that you will have species that have very few observations as well. And so, like right now, we didn't do any strategy for looking at the long tail distribution, but I think that's a recurring problem in many different applications that are about species distribution modeling.
Could you share a few thoughts on passive acoustic modeling? Do we just need to go drop little recording devices all over the key areas, or how do we get that rolled out?
Well, actually, so yeah, that's a simplified way of putting things. Yeah, people use a lot these audio moth devices. I mean, there are other types, but those are very popular because they're pretty cheap, and you just like tie them on a tree and then leave them there, and they record whatever is there. That requires a lot of hard field work because yeah, you want to put them in like places that are interesting, which might be in the middle of very difficult to access forest. It's like all this data that we're gathering, even now, I still feel there's a lot of things to study in, biodiversity monitoring with the data that we have. We are kind of more and more reaching a point where we actually have more data than we can analyze manually. So that's why, also ecologists are starting to really get into machine learning as well. Now, especially now that we have all those things like, recording passively or camera traps that take images or videos during very long periods of time.
Yeah, it's an exciting time for data collection, and I think the opportunity for computer science to be a contributor to some ecological scientific research. Could you share a few details on what's next for you?
Well, so I'm working on this extension of Satbird with Hager that was in the previous like a previous episode. Yeah, Sad Butterfly, and yeah, we're continuing this work on predicting species distribution from partial observations of other species. So this is a different setting because in this case, it's no longer the task of Satbird where the goal was really to say what is in a place where I have zero information about the birds there. This is more about saying, okay, I might have information about a certain subset of species. Now, what can I find? And this is actually something that ecologists, do when they're out on the field. Sometimes, they might not see a given species, but because they see something else, they can say that the other thing is present because they know that the two actually co-occur. Yeah, I'm also working on this project, which is about quantifying the carbon that is stored in tree plantations in Quebec from drone imagery. I don't know. I'm going to try and finish my PhD. I mean, the finishing the PhD is not you know, the main concern. It's more, oh, getting all those projects to a place where they can actually be useful to people other than just me. Yeah, I do hope in the future I can, really be a bridge between the computer science and machine learning and the ecology community. Also, give back to citizens as well.
Is there anywhere listeners can follow you online?
I have very little online presence. I mean, I do have a Twitter account, which is my first name and my last name all together.
Where can listeners learn more about Satbird, or maybe an ambitious ML person could get their hands on it and see if their technique is going to move the needle?
Oh, so we have a website called satbird.github.io, and you should be able to find all the information there and also my contact information.
Great. Well, I have links in the show notes for listeners who want to follow up. Thank you so much for taking the time to come on the show and share your work.